Welcome back, Pirates. Today what we're going to do is take a little bit of a closer look at these covalent molecules and see if we can understand a little bit about what's going on with these molecules based upon the atoms that are in those molecules and the arrangement of those atoms. Now this is going to get pretty complicated, so we're going to try to keep it as simple as we can by making some broad generalizations about some things that are not necessarily quite right in every single possible circumstance. And again, are kind of broad generalizations into big categories. But in an introductory chemistry class like this, it's going to suffice for us to be able to use these criteria to figure out a little bit about the discernment of some of these chemical and physical properties. So basically what we're doing here is we are looking at the sharing of electrons. Now, like the text says, sharing implies something about it. So here's person 1. And here's person 2, right? And let's say that they are sharing some manner of object. It doesn't even matter what it is, right? So there's a Mario star, whatever. I suppose it's got to be yellow if it's going to be a Mario star. They're going to share that, whatever. Okay. So in a implied statement with sharing, it means that this guy over here has it for a little while, and then this guy over here has it for a little while. And then this guy over here has it for a little while, and then this guy over here has it for a little while. And the idea here is that this is being shared equally, that the object in question is spending as much time on one of the people as the other of the people. But check this out. What if it did this? This guy gets it, and he holds 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 it. And then he hands it to this guy, and then he takes it right back, and he holds it, and he holds it, and he holds it. And he holds it, and he holds it. And then he gives it to this guy, and he takes it right back, and he holds it. Now, are they sharing? Yeah, they're sharing. They're just not sharing equally. So implied in the term sharing is that the sharing is being done equally. But in reality, it might very well be that that sharing is not done equally. Now, how are we supposed to know which ones share equally and which ones don't? How are we supposed to know which ones are kind of like the bullies, like this guy, right? Versus this guy who apparently can't keep the star for himself, right? So this guy over here is the bully. How do we know if he is a bully? Well, it is based upon a factor of each atom that is called electronegativity. Now, what is electronegativity? It's right here. It's the measure of an atom to attract electrons to itself. And that's a fairly simplistic look at electronegativity for a first-year chemistry student. If you're in advanced chemistry, it can get more complicated than that. Basically, let's just look at it like this. Electronegativity is how much an atom wants an electron. That's what we're looking at. Now, if we take a look at this chart, what do we notice about these guys? Well, we notice that once again that there are metals and non-metals, right? So this guy over here is a metal. These guys over here are your non-metals over here. Remember way back from the day, what do we know about metals? Metals want to lose electrons. And remember that non-metals over here want to gain electrons. So, is it very surprising then that the metals, which are all over here, right? The metals, which are over here that want to lose electrons, they have very low electronegativity values. By the way, I don't want to write out the word electronegativity anymore, so I'm going to use its symbol, and its symbol is like a scripty looking X that's here. So these guys have low electronegativity, and again, that's what that little symbol means if you see it. Electronegativity. See why I'm using the symbol there, right? So they have numbers that are very low. Notice over here, for the nonmetals over here, these guys over here have electronegativities that are very high. These guys have high electronegativities. Why? Because they want to gain the electrons. So if electronegativity is how much an atom wants to get an electron, right? How much an atom wants to attract an electron towards itself, then it makes sense that the nonmetals over here on the right-hand side have high electronegativities, and that the metals over here on the left-hand side, they all have low electronegativities, all right? So this was created by this guy here, Linus Pauling. He's a pretty smart guy. All right. So what have we got then? Well, let's take a look at some different examples of these guys and see who's being a bully and who's not. Let's start here with oxygen, right? Now, if we go back to our previous lesson, we can arrange the Lewis dot structure like so and end up with this Lewis dot structure for oxygen with a double bond in between and a couple of lone pairs on either side. So now what we do is we look up the electronegativity value of each of these guys on the table above. And if we look up oxygen here, right, here is oxygen. Erase all this. Here is oxygen. Apparently has a value of 3.5, which by the way is pretty darn high, right? The highest one is fluorine here at 4. Oxygen is in second place. Nitrogen and chlorine are in third places. It's not too much of a shock then to understand that these guys are all in the upper right-hand corner there. So anyway, oxygen here has an electronegativity value of 3.5. So we come down here and we recognize that oxygen has a 3.5 and oxygen has a 3.5. So who wins? Well, if this guy is 3.5 strong and this guy is 3.5 strong, then this guy on the left is no stronger than this guy on the right. And so what ends up happening is that this oxygen pulls the electrons towards itself, like that purple arrow shows, and this oxygen pulls it back like that purple arrow shows, and nobody wins. This is a classic tug-of-war example where everybody on the left-hand side is having a tug-of-war with their twin brother or sister on the right-hand side over there, and therefore that star in the middle there cannot move. And so what ends up happening is because there's an arrow to the left and an identical arrow to the right, you will learn a little bit more about this in physics, but these are called vectors, and those vectors essentially end up canceling each other out. So that arrow, which is directly to the left, cancels out with that arrow, which is directly to the right, and there are no arrows left. And so, consequently, if there are no arrows left, this guy here is considered to be a non-polar molecule. Ooh, new word there. Because the electron density is spread equally out. It is not shifted one way or the other. Let's take a look at a different example here. So, let's take a look at H and Cl. So here's H and Cl with their valence electrons 1 and 7, and we put them together and we make this Lewis dot structure here for H and Cl. Again, that was the previous lesson. And now we go through and we look up their electronegativity values. Chlorine is here at 3.5 and hydrogen is over here at 2.1. Well, who wins? Well, chlorine at 3 beats hydrogen at 2.1. And because it wins and wins so decisively, what we end up doing is we end up putting in an arrow, and that arrow is going to go from the hydrogen side over to the chlorine side because the chlorine side wins. So the chlorine is bigger. So this guy here is bigger than this guy over here. And because the 3 is bigger than the 2.1, we're going to go ahead and draw in an arrow over there. I'm going to go ahead and get you started on this idea. I'm going to put a little positive tail here on this guy because what's shifting over here are the electrons. So the electrons are spending more time over here on the chlorine side than they are on the hydrogen side. And hey, let's remember, what charge are electrons? Electrons are negatively charged. So there are more negatives over here on the right-hand side of this molecule than there are on the left-hand side of the molecule. So if that's the case, and it's more negative over here to the right, that must mean that it's more positive over here on the left, which is why I drew this little positive tail on my arrow. So what you end up getting then is you end up getting a shift of the electron cloud over here, and you end up with a negative on one side and a positive on the other side. New symbol for you. New symbol is this guy here, this little scripty looking thing that's almost an 8. That means partial. So that is a partial negative, and this over here is considered to be a partial positive. Because if it was a full negative and a full positive, we wouldn't be covalent anymore, we would be ionic. So what we've got here is we've got unequal sharing of the electrons within the cloud. All right, so here we go. New terms. Our new terms are this. Our new terms are polar. And what polar means is you have an asymmetric molecule with an uneven distribution of electron density caused by a difference in the electronegativities of the atoms. Huh? It means the electron cloud shifts to one side of the molecule. So what that means is it means the electron cloud shifts more to one side of the molecule. And if that's the case, then one side of the molecule is going to end up being partially negative, and the other side of the molecule is going to end up being partially positive. So there's not an even distribution of the electrons. So remember this guy up here? Remember how there was an even distribution of the electrons because nobody won this fight? This guy here pulled the electrons to the right. This guy here pulled the electrons to the left. They canceled out. And because of that, the electrons are evenly distributed throughout the molecule. Remember him? And because the electrons are evenly distributed throughout the molecule and nobody wins the tug of war, it is considered to be non-polar. There's no negative and positive in this molecule because everything is nice and evenly distributed. This molecule, however, we've got a bully and a wimp. And because this guy is a bully and this guy is a wimp, the electrons spend more time over on the right-hand side. And when they do, again, those electrons build up over here. And when those electrons build up over here, you end up with a partial negative on this side and a partial positive over on the opposite side. So there are three different types of circumstances that you will see. These are these broad classes of differentiations that I was talking about. They're not perfect, but it does give us at least a fighting chance to understand a little bit about what's going on with the polarity of the molecules. So here are the three possible circumstances that you could see. Circumstance number one is that it is an ionic bond. How do you know if it's an ionic bond? If there's any metal that's present, because metals don't do covalent. If there's a metal, it's going to be an ionic bond, and none of this stuff matters, because ionic bonds aren't polar or nonpolar. Ionic bonds are a totally different class. That would be like saying, how does a queen and a rook and a pawn move in checkers? Queens and rooks and pawns are usable in chess, not checkers. So trying to apply chess ideas to checkers is just not even going to work. So that's what I'm talking about here. Ionic means that you have a metal present. It's not going to be polar or nonpolar or any of that. It's a totally different game, okay? Now what we've got is we've got covalent, and either covalent is going to be either nonpolar or polar. How do you tell the difference? You're going to have a nonpolar covalent if your difference in electronegativity is between 0 and 0.4. You're going to have a polar bond if your difference in electronegativity is 0.5 or more. So here's what I mean by that. Let's take a look at S and Cl. Here's S and Cl. First of all, they are nonmetals. S here and Cl here. And because they're nonmetals, it's going to be covalent. Remember, if it's ionic, if there's any metal that's there. So because S and Cl are there, it is going to be covalent. Now the question is that individual bond going to be polar covalent or nonpolar covalent? And if it's polar, which way does that arrow go? Well, let's take a look. We looked it up already. It's 2.5 and 3. So the electronegativity of S is 2.5. The electronegativity of Cl is 3. So what we're looking for here is we're looking for the difference in the electronegativity. It doesn't matter what the number is, it matters what the number is compared to the other number. So if I subtract 3 and 2.5, then I get the number of 0.5. So 0.5 is here, and 0.5 is in the polar category. So what I would do then is I would draw in an arrow, and I would draw in an arrow to whichever one is bigger, and it looks like I have an arrow that's going to go from the sulfur to the chlorine over here because the chlorine wins. So in this bond, I would draw an arrow this way because the sulfur is 2.5 and the chlorine is 3. Okay? So all you have to do is find out where on the periodic table these things are and what their electronegativity values are. Let's try the next one. The next one is lithium and iodine. Here's lithium and here's iodine. As soon as we look up lithium, we discover that lithium is over here in the metals side of things. None of the numbers matter at this point. As soon as you see that this guy here is a metal, you're done. This guy is a metal, you're done. This guy is ionic. You don't have to do any math, you don't have to do anything. This guy doesn't follow covalent rules. This guy follows ionic rules. Okay? So, moving on to the next one. I don't have to do anything with numbers on this guy because that guy is a metal. The next one, I've got H and I've got O. All right, let's check those guys out. Here is H and here is O. All right, so H behaves more like a non-metal in these circumstances than a metal. Remember, H is a little bit of a goofy wild card. So we'll count him as a non-metal. And then we look up their values, 2.1 and 3.5. So because there are only non-metals in this, it's going to either be non-polar covalent or polar covalent. So all we have to do now is look up their electronegativity numbers that are there. So their electronegativity numbers are 2.1 and 3.5. So 2.1 and 3.5. Between those guys is the difference between them is 1.4. So that's a really big difference. So what you're going to end up with then is an arrow that goes from the 2.1 over here to the 3.5 because of that. So once again, that is a polar covalent situation that's there. All right, a couple more, then we'll move on. This guy here. This guy here is carbon and sulfur. So here's carbon and here's sulfur. Here's carbon and here's sulfur. They're each at 2.5. So if I subtract 2.5 from 2.5, I get a value of 0. And remember, if the difference is anywhere between 0 and 0.4, then it's considered to be a non-polar covalent bond. And for a non-polar covalent bond, I don't even bother to draw an arrow. So that guy there is non-polar covalent. All right, last one of this bunch. What about strontium and chlorine? Strontium is way over here, chlorine is way over here. As soon as you see that you've got a guy over here, I don't care what the numbers are, this guy is going to be ionic because he contains a metal. The numbers don't matter. All right, so to summarize this, and we're just about done. To summarize this, if there is a polar covalent bond, you draw an arrow. If there is a non-polar covalent bond, you draw no arrow. And if it's ionic, you don't even bother with any of this because this won't apply to ionic. All right. So, why does this matter? Well, check it out. Molecules can get pretty complicated. So if we check out this carbon dioxide and come up with the Lewis-Dot structure for this, and again, that was from the previous lesson, we can now look up the electronegativity values of carbon and oxygen, and we can see that the electronegativity values of carbon and oxygen are here at 2.5 and 3.5. Ah, okay. Well, let's check those out. So this carbon is sitting here at 2.5, and this oxygen is sitting here at 3.5. What I do is I subtract those numbers to get my change in my electronegativity, and 3.5 minus 2.5 is 1. 1 is a pretty big difference, and remember that if your difference is 0.5 or more, I'm going to go ahead and draw in an arrow. So I'm going to come down here and I'm going to draw in an arrow that goes from that carbon to that oxygen. But don't forget that you also have an oxygen over here. And so the difference between here and here is also 1. So what that means is I'm going to have to draw in an arrow from here to here. Now wait a minute. What are those arrows doing? They are pulling in opposite directions. And what did we learn before when we have arrows that are equal in magnitude but opposite in direction? Remember back here with our oxygen? Remember back here with our oxygen that if we had an arrow going this way and an arrow going that way, equal in magnitude but opposite in direction, they canceled out. So what happens here is that these arrows, the one I drew here and the one I drew here, they end up equal and opposite, so they cancel each other out. And if there are no molecules there are no polar bonds left in this molecule, then it is considered to be a non-polar molecule. Oh my goodness. But it has polar bonds. I know. That's what makes this complicated. So, this is a molecule that has polar bonds, but is overall non-polar because all of those polar bonds cancel each other out. So, non-polar molecules come from either having bonds that are non-polar or having polar bonds that cancel each other out. I'll summarize all this later. Let's check out another example. Here is water. I just went ahead and gave you the Lewis dot structure and looked up the electronegativity values. So I've got 2.1 and 3.5. So the difference between that is 1.4. If it's at least 0.5 or more, you draw in an arrow. So remember, if it's 0.5 or more up here, we're going to go ahead and draw in an arrow. All right, so I'm going to go ahead and draw in an arrow for this guy. And that arrow is going to go that way. But I also have an arrow that is this way. Now, do those arrows cancel each other out? Well, are they opposite of each other? Well, no, they're not. They're actually both pushing over towards the oxygen over there. And because they're both pushing towards the oxygen over there, that is going to push all the electrons towards that oxygen. So the electron cloud is going to go here, or the electron cloud is going to go here. And because all the electrons are over here on the oxygen because it got shifted, that makes the oxygen side over here the partial negative, and it makes each of these hydrogens over here a partial positive. So in order for them to cancel out, they have to be exactly opposite of each other, and they are not. They both push over to the oxygen there. So this guy is considered to be a polar molecule. So here are the summaries of the rules that are here. First up, you look up the electronegativity. Determine if they're polar or nonpolar. If they're nonpolar, don't draw an arrow. If they're polar, draw in an arrow with the arrow pointing towards the bigger number. If you have ones that are equal in magnitude and opposite in direction, you can cancel them out. If there are any vectors left, then it's polar. Excuse me. Goodness, so sorry. If there are no remaining vectors left, then the molecule is non-polar. All right, so check this guy out. Here is carbon tetrachloride. I've given you the Lewis dot structures, and I've given you the electronegativity values. So between 3 and 2.5, that is a difference of 0.5. And 0.5 is worthy of drawing an arrow. So if it's worthy of drawing an arrow, then I'm going to draw an arrow up to there, but I'm also going to draw an arrow down to there. Hey, guess what happens with those arrows? One up, one down, they cancel each other out. I'm also going to draw an arrow over here, and I'm also going to draw an arrow left and right. Those are equal and opposite, and so they end up canceling each other out. So this is a molecule that has 4 polar bonds, But all four of those polar bonds cancel each other out, and there are no arrows left. And if there are no arrows left, then this is a molecule that is non-polar. So that's a molecule that has polar bonds but is non-polar. This is a molecule that has polar bonds but is polar. This is a molecule that has polar bonds but is non-polar. So you can see that it gets fairly complicated here. So like it says here in your steps, you have to look up the electronegativity values, determine if they're polar or non-polar. If they're non-polar, don't draw an arrow. If they're polar, draw an arrow. Cancel anything out and then see if there's anything left. If there's any arrows left, it's polar. If there are not any arrows left, it's non-polar. One more example. Check out this guy. All right, this guy's getting kind of complicated, right? Well, let's check him out. I've got a 3.5 and a 2.5. So the difference between here is 1.0. That's worthy of drawing an arrow. So I'm going to go ahead and I'm going to draw in an arrow from there to there. Now let's check these guys out. 2.5 and 2.1. Well, the difference between 2.5 and 2.1 is only 0.4. Remember, way back up here, if the difference is only 0.4 or less, remember this guy? If the difference is between 0 and 0.4, you don't even draw an arrow. So there's no arrow to be drawn. If your difference is 0, 0.1, 0.2, 0.3, or 0.4, you don't draw an arrow. So we're going to come down here again, and the difference between here and here is only 0.4. So guess what? I am not going to draw an arrow. Nothing. No arrow here. No arrow there. I'm also then going to not draw an arrow here because the difference is 0.4, 2.5 to 2.1. So check it out. Those are all three of my bonds. I've only got one arrow in this molecule. It's from the carbon up to the oxygen. There's nothing to cancel that arrow out. And so if there's nothing to cancel that arrow out, then that means all of the electrons in that bond shift up here. And if all the electrons in that bond shift up here and they spend more time up here than they do on the other side, then that means we have a polar molecule with the negative at the top and the positive at the bottom. Because again, those electrons are spending more time up here than they are down below. So this gets complicated and it's going to require a little practification on your part. But if you go through the examples that we have in the homework, you should be able to determine whether or not these are polar or non-polar. So again, there are two things that you need to make sure that you have access to. And that is this guy here and an electronegativity chart. Yes, you will be given those on the quizzes and the tests. So if you have that guy and that guy, you should be able to answer all of these questions. Find out if we need to draw an arrow. If we do, draw them in. Draw in the arrows. See if they cancel out. If they cancel out, non-polar. If they don't cancel out, polar.